All right. Welcome to lesson 2 of probability distributions, discrete probability distributions, because that's what we do in year 11, discrete probability distributions. And lesson 2 is about expected value. So expectations, there are two lessons, two mini lessons in this particular video slash lesson. First of those is something that you've done before in previous years, and it's just expectation, it's expected value in general. So a question like this: a dice to be rolled 120 times. On how many occasions should we expect the result to be a 6?
20 times.
20 times? How did you do it, Salman?
1 over 6 times 120.
So I just did it in my head, like that's common sense.
I thought you did it in your foot. Obviously, you did it in your head. I want to know how you did it in your head. What did you do?
He's trying to be funny on YouTube.
1 over 6 times 120.
Quick, Salman, what did you do?
I'll tell you,
I
sir.
said it. 1 over 6 times 120.
Bro, he asked me, not you. Sir, 1 over 6, because we know 6 has a 1 over 6 chance.
Thank you, Tahir. Well done. Okay, so we find the probability of getting a 6, 1 out of 6, and we multiply by how many times we're going to do the experiment, 120, and that equals to 20. And yes, that's correct. That is what we do. And just in case someone isn't sure, this is my explanation. You can look through it later. Let's not waste time on stuff you already know and move on to something that is new. All right, so if you want to find the average, now this is just a general note so that you don't get confused afterwards. If you want to find the average of the numbers 7 and 8, you would get 7.5. The average, the mean of 7 and 8 is 7.5, right? Now, the mean, the average is not 7 and it's not 8, it's 7.5. 7.5 is neither of the original values, but does that make a difference? No, it makes no difference whatsoever. We're just trying to find the average, okay? Just keep that in mind, because some students get confused when you find the average value. So for example, if you try to find the average score or the expected score from rolling a die, you would get 3.5. And many students are like, well, hang on a second, you can't get 3.5 if you roll a die. Well, it doesn't matter. We're just talking about the average score, the expected value. What is the average score if you roll a die? If you do 1 plus 2 plus 3 plus 4 plus 5 plus 6, you divide the whole thing by 6, you would get 3.5. And that is the mean of the numbers 1 through 6. And it makes no difference that it's not any of the original values. It's irrelevant. Any questions about that?
So for average, you just divide it, add them and divide?
Yeah.
Yeah, and for what's the other one?
There is no other one right now.
Oh, no, okay, got it.
Any questions about the fact that the mean, the average of set of numbers does not have to be any of the original numbers?
Yeah.
Okay, moving on.
So for dice, how you only get 3.5?
Well, you're not. That's the point. It doesn't matter that you can or you can't,
Okay.
but it's still the average score. If you roll a die, on average, you're going to get 3.5.
I got it.
Because you can get a 1, you can get a 2, you can get a 3, a 4, a 5, or a 6. If you add all of those up and you divide by 6, then your average score is 3.5.
Yeah.
Okay, the average score is 3.5. It doesn't matter. No one is saying that you're going to get 3.5. It's just that's your average score.
Yeah, got it now.
Like, for example, if Salman got 7 and you got 8 in a test out of 10, and I said, what's the average score? The average score would be 7.5. Now, it's irrelevant whether someone actually got 7.5 or not. That's not the point. The point is simply that that's the average score. It's just a number. It's a value. It's a statistic. It tells you the average score.
Yeah, got it now.
Okay.
Yeah,
yes,
but that was hypothetical, right? Because you accidentally said Tahi got high didn't mean the test.
Yeah, it was hypothetical. That's right.
Oh, good.
All right, moving on. So now the question that's facing us today is, how can we calculate the expected outcome when the probability of each result is not equally likely? Like in lesson 1, the one we did yesterday, where we rolled a die. No, we flipped the coin 3 times and we said the number of heads. Now the number of times you get head 0 is 1 over 8. Then it was 3 over 8, 3 over 8, 1 over 8. The probability of each outcome was different. So how do you find expected outcome there? So let's get started. The random variable x has probability distribution as shown in the table below. So let's say, hopefully this reminds you of lesson 1. The first row tells you all the possible outcomes The second row tells you the probability of getting each outcome. So you can get a 1, the probability of getting a 1 is 1 out of 10. You can get a 2, and the probability of getting a 2 is 1 over 4. Or to be, I guess, to be more mathematically accurate, x can take the value, the random variable x can take the value 3, and the probability that it does so is 1 out of 10. The random variable x can take the value 4, the probability that it does so is 1 out of 4, and so on.
Sure.
How do you find the expected value of x? We can write this in short as E of x, so keep that in mind. E of x is the expected value of x. This is very similar to the notation P of x, which is the probability of a certain event x, like, if you write P over A, the probability that event A occurs, right? E of x just means the expected value of the random variable x. What is the expected value? What do we expect? The average score, so to speak. And the formula for calculating expected value is simple. You multiply x and P of x value. So multiply these two together, and then you multiply these two together, and you get an answer, whatever. And you multiply, when you multiply the orange stuff, you got an answer. You write it down over here. Multiply these two together, you write it down here. Multiply these two together, you write down here, here, and here. And you add all of them up, and your expected value is going to be here. The sum, this is the sum of all of these, and that's your expected value. Okay, so in words, we multiply x and P of x equals to x for all the values of distribution. So x and P of x equals to x for all the values of distribution, and then add them up. Okay,
Sorry, what do you mean?
So you add you multiply these two,
yeah,
you get an answer there.
Yeah.
You multiply these two, and you
like the
get an answer there, and then you add all of these ones together. You add those up, those fractions, you add them all up, and that's your expected value, and you write it over there.
Yeah, got it.
Okay, now you can do it like this. 1 times 1 out of 10, 1 times 1 out of 10, plus 2 times 1 over 4, plus 3 times 1 over 10, plus 4 times a quarter, plus 5 times a fifth, plus 6 times a tenth.
Yeah.
And that is equal to 7 out of 2. So our expected value of the random variable x is 7 over 2. Not 7 out of 2, 7 over 2. Okay, now just as the mean of a set of whole numbers isn't necessarily a whole number, similarly, the expectation of a random variable need not be one of the values that the variable can take. Now, we said over here that the random variable x can take on the value 1, 2, 3, 4, 5, and 6. And we're saying expected value is 7 divided by 2, 3.5. Even though the random variable x cannot take on the value 3.5, it doesn't matter. This is simply a statistic.
Yeah.
It's the expected value, exactly the same way as we were doing in the previous slide. So don't get confused. It's just expected value. That's our expected score. Moving on.
Yeah.
Find the expected value of the following set of data. How would we do this? What do we do?
So
Wait, so my bad. So I was on mute. So you do 1 times 0.23 plus 2 times 0.38 plus 3 times
Good.
0.21 plus
Is equal to 1 times 0.23 plus 2 times 0.38, and then so on and so forth. And you get something like that,
yeah.
which is equal to 2.39, and you're done.
So is that all for
Well
today?
done. Any questions? I'll pause here for a second. So if you have any questions whatsoever, ask now.
That's it. Is there any more that we need to cover?
Oh, this is pretty much it, but I'm just going to cover how we're going to set out our work.
Okay.
So here's one way to set out our work, and we're going to continue the example from yesterday. If you flip a coin 3 times, what is the expected number of heads when we've tossed 3 coins? Okay, so that's the tree diagram from yesterday, and this is what we had yesterday. Hope you remember. And what we've done today is another row where we just multiply these two together, and we write it over there. 0. 1 times 3 over 8 is just 3 over 8. And so you're multiplying these two, and you can see the x times p over x. So x times p over x. And we write it in this row. You add these up, and you get the sum.
Okay.
And that is our expected value. So that's e to the x is 1.5.
You got it.
Any questions?
No.
So it's important that you sum up the middle row. You sum that up and make sure it's equal to 1. It's just a quick check to make sure you didn't make a mistake with anything. It has to equal to 1 because these are all the possible values that the random variable x can take. This is the probability associated with those values, and they have to add up to 1 because that's literally everything that's possible.
Yeah.
We've covered everything that's possible. It has to add to 1. Doesn't add to 1, you made a mistake somewhere. And then obviously you multiply it down and then you add together. That's the expected value. Okay.
Yeah.
All right, moving on. And a die is thrown, find its expected value. Well, that's pretty straightforward. Hopefully you can see, make sense of this.
Yeah. 1/6 times 1, 2/6 times 2, 1/6 times 2. Yeah.
Yeah, and you add them all together, and obviously
Yeah,
it's 3.5.
3.5.
And so our expected value from rolling a die is 3.5. Do note, expected value, we write it like this as well, but generally you write like this. You have x. And once again, 3.5 isn't a value that a die can take. It doesn't matter. It's irrelevant. It's got nothing to do with anything. We're just speaking about a statistic, the expected score. The expected score, if you roll a die, it's a statistic. Okay.
Yeah.
All right. So expected value, because it is the mean score. Expected value is just a fancy name for the mean of the distribution, the average of the distribution. And we know that the mean of a set of numbers is usually not one of the numbers. Any questions?
No.
All right, moving on. This is probably as hard as it gets. 20 friends go out to dinner at a restaurant. One has $506 cash. 4 have $350 cash. 2 have $180 cash. 3 have $80 cash. 4 have $50 cash. And 1 has $40 cash. 5 have no cash whatsoever. They're expecting to borrow from the others. So who's like that amongst you guys? Who's the one who's always borrowing? Actually, you know what? This is going to go on YouTube. Don't answer that. An armed robber bursts in and seizes one of the friends at random. She threatens him, grabs all his cash, and runs away. Find her expected criminal gain. And I guess the idea is as follows.
So what you do is you do 1. The first one is going to be 1, and then 560, and then 2 would be 180. 3 would be $80. 4 would be $50.
Well, we have to do it from in ascending order.
Yeah, and 1, I forgot about 1.
Do note that we're looking at expected criminal gain. And so how much money is she going to get? What are the values of money that she can gain? And we have to do it in ascending order. So what's the first amount that she can gain?
So I'm confused. How do you go from borrowing money to a criminal gain?
Don't worry about borrowing money. 5 have no cash and are expecting to borrow money from the others. 5 have no cash is the important bit here. See, okay, look, okay. The way I would approach this question is as follows.
5 have $0.
We're trying to find the expected criminal gain. There's this robber, a thief, right? An armed robber bursts in and takes all the cash, steals all the cash. So seizes one of the friends at random. The robber doesn't grab the cash from everyone, just seizes one of the friends at random. Okay, one of these at random, one of those people at random. Not all of them, just one of them. And so it's kind of like probability because she could have chosen any one of them. She or he, whatever. Yeah, so it's a she. Find her expected. So she says, yes, the robber is a she. She finds one of those people at random. What is her expected criminal gain? So she could have chosen anyone, which means that she could have a random amount of cash. So we're going to write down the amount of cash that she could have had. We're going to write down the sample, the sample, what's it called? Sample space. We're going to write down all the possible outcomes. She could have had $0. Okay, so if we were to draw a graph, and that's X, and we're going to do P of X in a second. P of, I think, what was it, like this? Equals to that. And we're gonna fill it in a second, but she could have had 0 and no cash. So if she chose one of the people who have no cash, she would get $0. She could have had $40 as well. Okay, so I won't write dollar sign, I'll just write 40. She could have chosen the one with $50. There's 4 of those. Okay, fine. 3 have 80, and then 180, 350, and I think it is 560. Okay, this is all the possible amount of cash she could have had. Any questions so far?
No.
All right, so what's the probability that she got $0? Well, there's 5 people without any cash. Now, if you sum up all the different, how many people actually went out, 20 friends went out. So it's going to be 5 out of 20 people had $0. So probability that she got $0 is 5 out of 20.
1/4.
Yeah, which is 1/4. We're just going to leave it 5/20 for the time.
Oh, okay.
And how many people had $40? 1 out of 20. So 1/20th chance that she actually got $40 only. And then you have 4/20th chance that she got $50, and 3/20th chance that she got $80, 2/20th chance that she got 180, 4 out of 20, 1 out of 20. Okay, now we do have to add these together. 5 1 is 6, and 4 10, 13, 15, 19, and 20. So when we sum it up, we do get, I can't go any further right, please. That's 1. Okay, so when we add these up, we got 20 out of 20, which is 1. So I know I did not make a mistake.
Yeah.
Yeah. Any questions?
No.
Okay, now to find the expected value, we do need to multiply x times p of x equals x. We'll multiply these together.
Yeah.
Right, so x p of x equals to x. Just write like that. You add them, multiply them all down, and I don't want to draw all over again. So yeah, you get something like that. Yeah, 0 times 5/20 is obviously 0. 40/20 is going to be 2, and so on and so forth. And so our expected value is $140. Her expected criminal gain is $140.
But how? She takes from only one guy.
Yes, she takes from one guy only, but her expected criminal gain, her expectation, her expected value, because she could have gotten 560, she could have gotten $350 as well. It's just a statistic. It's just the expected value.
Yeah, got it.
Okay, so $140 is the expected value here.
Yeah, makes sense.
Okay, I believe. Yes, in gambling, we say that the expected gain of the player from each game is the expected return or payout from the game, less the amount it cost them to play. That's very important. So the game will be fair if the expected gain is 0. So for example, in a game of chance, a player spins a square spinner, labeled 1, 2, 3, 4. The player wins if the amount of money shown in the table, the player wins the amount of money shown in the table below, depending on which number comes up. Determine the expected value on one spin of the spinner, and therefore whether you would recommend someone play this game if each spin costs $5. So you have a spinner, you got to pay $5 to play, and when you do play, okay, sorry, okay, so I'm just gonna put it all up. So the value, the expected, okay, you have a spinner labeled 1, 2, 3, and 4. You spin it, and you can possibly get 1, 2, 3, or 4, and you win $1, $2, $5, or $8. So I guess it's not very clear. The graph could have been drawn better. My bad. But anyway, you can get 1, 2, 3, 4. So I guess you can write it like this. Where is my pen? So you can get 1, 2, 3, 4, and this is how much you win. Okay, so winning amount is you can win $1, you can win $2, $5, or $8. Any questions so far? And the probability that you will get each of those is 1/4, and then the expected value multiplied down. Expected value is $4. So you can expect to win $4. But how much does it cost to play the game?
So yeah, lost me there. Where's the 1, 2, 3, 5, 8 come from?
Okay, so you have a square spinner labeled 1, 2, 3, 4, right?
Yeah.
So 1, 2, 3, 4. And the player wins the amount of money shown in the table below. So if you get a 1, you win $1.
So that's
If you get
table.
a 2, you win $2. If you
Okay.
get a 3, you win $5. If you get a 4, you win $8.
Okay. Yeah.
And because it's a square spinner and all of them are equally likely, you get a quarter probability for each one to happen.
Yeah.
And so your
Uniform.
expected value is going to be $4.
Yeah. Okay.
Yeah.
Yeah.
All right, but it costs you $5 to actually play.
So you're gonna lose either way.
Well, yeah, you expect to lose $1.
Yeah.
Right, so expected return is $4 short, but it takes you $5 to play, so you have to subtract $5 for the amount for each spin, and the game is clearly not worth playing. You can expect minus $1 for each spin. And this is kind of how gambling works. If you go to a casino and so on, which will never go, but if you ever did go to a casino and you gambled, they say the house always win, which basically means all the games are rigged. Sure, you can get lucky. It's kind of like lotto as well. You have millions of people buying tickets for the lotto, and sure, one of them might win $1 million or whatever. But at the end of the day, those lotto companies, they earn so much money because the chance of you winning is less than the chance of you being struck by lightning. It's crazy. It's very, very, very small probability that you'll win. And people say, "Oh, but I might win." But they don't really know the likelihood. It's more likely that you guys will become the president of the United States than it is that you'll win the lotto. I was watching this video the other day, and it's more likely that you'll be struck by lightning twice in a year than that you'll win the lotto. Because that's how they design these gambling games. They're in it to make money. They're not there to help you become rich. They're trying to become rich themselves. And they kind of sell hope, if that makes sense. Anyway, so yeah, it looks like if you didn't know maths, didn't know statistics, you'll be like, oh, you put $5 in, you might get $8 back. Oh, hey, that's a good opportunity to get rich, right? But actually, no, every single time you enter this game, you're actually going to lose $1 expectation. So maybe in the short run, you might get lucky and you might spin it 3 times and you'll actually win every single time. It's possible. Right, but over the long run, we expect to lose $1 for every single time you spin. So over the long run, if you spun this heaps and heaps times, then you would pay $5 each time, and you would expect you to get back $4 over the long run on average. So hopefully that makes sense. If you invested like $1,000, you'd get back $800 over the long run. Over the long run. Okay, so that's not a fair game because you expect them to lose. Okay, now this is probably the last thing for today, which is sigma notation. There's a symbol in mathematics called sigma. It looks like this. We just say sigma. All it really is just sum. It's just shorthand notation for sum. It means the sum of, and it's used in the following way. And hopefully I'm going to try and explain. Please try and pay attention. I believe your textbook uses it. It's not technically part of the syllabus, so I wouldn't worry too much about this. It's not going to appear in the HSC at all, but it just makes it easy. It's going to appear in some other textbook exercises as well. It's worth learning. It's pretty straightforward. Look, what we're going to do is we're going to sum these up. You're going to sub in 1 first, and then into this. And then you'll be like plus, and then you'll sub in 2. And then 3, and then 4, and then 5, up to 6. That's the last value you sub in. Okay, so let's say, for example, you have that. K equals 1 is what you start with. So we sub in 1 into K, you get 1. And the right plus here. And then you sub in 2. You do plus. And then you sub in 3, 4, and then 5. The last number you sub in is 5. Then you add them all up. Any questions?
No, I don't get it.
Okay, so for example, that's horrible. Hang on a second. So if we do, let's say we're subbing into here. That's what we're going to sub into. And we're going to sub in n is equal to, the first number we're going to sub in is 10. The last number we're going to sub in is 13. Okay, so let's just evaluate this. What is the value? What is this equal to? So what we do is we say this is equal to 2 times n. The first value of n we sub in is 10. So you sub 10 in. Then you do plus. And then now this is going to change you can think of this as going up. This is going to count up all the way up to 13. I'm going to submit 11 now. 2 times 11 plus, what do I submit now?
12.
12.
13.
And then what do I submit?
13.
And then what do I submit?
I don't know.
Nothing, because we're done. We have to count up to 13. And that's it. We're done. And you just evaluate that.
Okay.
Okay, so that's it. That's what this notation means. You start here and you end there. Okay, and the reason they've introduced this notation is that we can write the notation for the formula for x-restricted value as this: sum of x times p of x. So you know how you had a bunch of values in the third column and you had to add them all up to get your expected value? It's just a shorthand notation for this. This is just shorthand for what they want you to do. Just add all of them up. When you see the questions in the book, I guess it'll be, like I said, it's not in the syllabus, so I wouldn't focus on it too much. If it pops up in the textbook, you're not sure, let me know and I'll try and explain it. But that's it for today. So I'm going to end the video here.